Yeah, hello everyone. My name is Rob. I work for Parity Technologies. So some of you might know about Parity already. If not, I'll give a brief description of what we do, which is what we would call core technology. So things like Ethereum clients, but also just lower level applications or infrastructure projects that other apps can leverage. So today I'm going to be talking a bit about our Ethereum client, specifically the Light client framework. So I would break this down first into defining. So I would put this down first to defining different classifications of Ethereum clients. So first we have our basic full nodes. So what full nodes do is they download every single header, every single block, they execute them all in order, starting from the genesis, make sure that not only is the consensus done correctly, but also all the transactions execute correctly and all the data checks out. So this is actually a fairly heavy operation. And if any of you have tried to run a full node recently, you might notice that this is using a lot of storage on your computer, a lot of CPU, a lot of memory. So then the next level down would be light clients. So that's primarily what I'm going to talk about today. So what a light client does is it just checks the block headers. So it starts at the genesis, say, and downloads all the headers starting from there, and it verifies that consensus has been done correctly. But it doesn't execute the transactions in the block, so it does lose a little bit of information along the way and perhaps a little bit of security. And the last classification of Ethereum clients is one that I would call thin clients. So a thin client is basically just a wrapper around a remote node. So you have a website that knows a node somewhere else, and it just asks it for data, unproven about the state of the Ethereum chain. So if we talk about the security guarantees of a light client, it checks the validity of headers, so it checks the proof of work, or perhaps once Ethereum moves to proof of stake, it would check a signature by some authority or validator. But it doesn't check the validity of state transitions, that transactions have been executed correctly, or that block rewards have been given out. So to think a bit what kind of attacks this leaves us open to, we have to think about the behaviors of other nodes on the system. So first of all, we have an honest majority assumption with the miners. So if you take this assumption that the majority of miners aren't going to be producing invalid blocks, then unless you have some other miner directly targeting you and sending you invalid blocks, you won't be able to see invalid blocks that have those invalid state transitions, which you wouldn't be able to detect as a light client. So that leaves us open to a very targeted sort of attack where you have an attacker who knows that you're running a light client, and for whatever reason it's valuable to him to take up all your peer slots and start sending you invalid blocks to try and fool you into sending a transaction that you don't want to. Because another thing that can't happen is for him to trick you into thinking that well, actually, that's not correct. So he can fool you into thinking that the current state is different, and he can send you proofs on that. But if you do go back and check that the transactions have been done correctly, which you would if you have a high-value application that's running, you cannot be fooled. So we have a goal when we're designing our network protocol. So the first goal is to minimize the round trips and bandwidth. So we have a few core pieces, one of which is back referencing, the second of which is to check state proofs, and the third of which is a pub-sub network protocol. And the goals are really to leverage that security assumption of the Ethereum chain as highly as possible. So we've checked the consensus, and that means that we trust some block header hash. This block header contains a state tree root, and we want to say that any state data that we read from the chain can be provably connected to this state tree root. So we design all of our requests around this provable data. And the last thing is we want to think about avoiding denial of service or just spam of protocol servers. So when you're a light client, you have to ask your peers, prove this data exists in the state right now. And if we don't have some kind of layer to prevent people from making tons and tons of requests, it could be that the protocol servers are overwhelmed by that. So we want to think a bit further in the future about things like micropayments, and we would leverage technology like state channels, for example, to make those micropayments very small, but actually provide an economic incentive to serve that data. So to speak about back referencing, this is, I think, a really critical part of that light client protocol, because as you recall, we don't have the state. So we might want to fetch a block header, and then from that block header, get a state proof of an account's existence. And then we have, from that account structure, we can get a reference to another Merkle tree which stores the storage for that contract. So we have 3 pieces of things that we want to fetch. We want to fetch the header, then the account, and then some storage. So that actually logically requires 3 requests. But imagine if you have a 100 millisecond latency with your peer. If you go there and back and there and back and there and back, that's 600 milliseconds of latency. And that's actually a very long time to make a simple contract call to your peer. So we have this idea that we have heterogeneous requests embedded in a single packet where the later requests in the packet can reference data that's output by the prior. So in this way, we can do these 3 requests, or basically any other kinds of requests. For example, even smart contract executions, they're very composable. We can do all of that in a single round trip, and it's still provably secure, but you get a much lower latency, and that's a better user experience. So to speak a bit more about these state proofs, we have a state tree here, right? So that root of that tree, the very top node, is embedded into the block header through a cryptographic reference. And when we execute a Turing-complete smart contract, it's actually unpredictable which pieces of data we want to fetch from that state tree, because it requires execution of arbitrary code. So if you are using a light client and you want to, say, do an Ethereum name service lookup, like this might require fetching all kinds of different pieces of data from the network. And if you were just executing it locally, and every time you need a piece of data to go to a peer and ask, give me this account, give me this storage, it would actually take a really long time. So the second aspect of our minimizing round trips goal is to do entire transaction state proofs, so that when you want to see what the result of a call would be prospectively, you can just ask a peer, prove this call to me, and not just do it piecewise, which is too inefficient. And the last thing is we introduce a model of something called request credits. So these servers give the light client peers little credits that can be used to make requests. So credits might recharge slowly over time. This is how it works now. So every time you want to make a request for, say, a header or a piece of the state, you use a little bit of these credits. And different servers will have different costs. It'll be based on, their empirical measurements of how long it takes to serve a specific request. So that makes it adaptive to improvements in storage hardware or growth of the Ethereum state, etc. So this is actually a pretty generic scheme that can be used to leverage micropayments as well. So instead of having them recharge over time, when you pay a server, they give you some request credits. So the last thing we want to think about is this concept of a publish-subscribe system. So our full node peers, as a light client, know a lot better when something has changed in a contract than we do, because we just don't have that state, and it's fairly bandwidth intensive to download the updated state every block. So if we can introduce a publish-subscribe system, our peers can push that data to us as it's updated. But the hard part is there's no real way to check if a full node peer has just skipped sending us something that has changed. But what we can do is also farm out requests to multiple peers, and if they differ, perhaps there can be some kind of on-chain dispute resolution where a bond gets slashed. But this is definitely an area for open research. So another optimization that we have in the light client is this idea that we shouldn't have to store all the block headers from the genesis up until now. It's something like 5 million or so now. It's just going to keep growing. So that's a lot of block headers to keep around. So we have an idea that we can instead store a mapping from block number to the hash of that header and the total difficulty of that header in the form of a Merkle tree. But we actually split this mapping up into several different pieces, and once every n headers, like n is 2048 or 4096. And so we have blocks from 1 to 2048 all in one of these mappings, and after we've passed that block on the light client, we just generate that mapping locally and throw out all those headers. And we keep that mapping in a Merkle tree and keep the root of that. So that means that if we have any full node peer who has the same history as us, they can also generate that exact same Merkle tree and prove the header hash of any block in that history to us. And that allows us to keep, say, 2048 blocks, well, a reference to them in only 32 bytes. So if we ever want to get those historical blocks, we can do so securely, but we don't have to keep them ourselves. And warp sync is really important because light clients are a lot faster because they don't have to do this heavy operation of executing the transactions and regenerating the next state tree. To apply those updates is actually very heavy. It's really the bottleneck for full nodes right now. But even so, initial sync can be fairly slow. If you start at the genesis and you verify the proof of work for 5 million headers, it's going to take ages. So we have to think about other ways to sync. So warp sync is this idea that you can jump directly to the head of the chain with some level of security. So on proof of work, this is possible with thin client security. So at the very beginning, we just sort of get a trusted header hash and start from there. So we can't actually validate anything about this header hash. But then once we've downloaded the ancestry leading up to that, and we can do that in the background, we have a much higher security level, which would be equivalent to a typical light client security level. After this EIP 96, which makes some changes to how historical block hashes are stored in the state, we should be able to do proof of work, warp sync, as well as under proof of stake systems or proof of authority systems to do a warp sync with full light client security from the very beginning. And that ancient block download can then be done on the background, potentially only on Wi-Fi. And I would say a fast and secure warp sync, or just the ability to get to the head of the chain quickly, is really crucial for introducing a micropayments-based scheme, because you can't actually enter into any kind of state channel contract unless you're already at the head of the chain, which means that full node peers would have to serve those blocks, those block headers necessary to synchronize for free while serving other requests for a cost. And that's a strange balance in the model because it opens up servers to spam very easily. So one final distinction I would like to make is that secure warp sync is different from having a hard-coded header hash or something equivalent to that in the client. So one thing you can do in a client is just say, when you make a release, we hard-code the latest hash of the chain. We say, OK, light clients, pick up from here. And that requires an additional level of trust in the developer, as opposed to a trustless warp sync where we're relying on cryptographic properties. So to speak about micropayments a bit, this is essentially the scheme that we have. So a light client and server open a state channel between each other. The client pays the server for every bit of data, and that can only really be done at the head of the chain. Because until you trust those headers at the head of the chain, you can't interact with any smart contracts there reliably. So our idea for how people can use this light client is actually very flexible because we've written it in Rust. And Rust is very flexible in terms of where we can compile and deploy it to. So right now we're building the light client for Android and iOS. It can be embedded in mobile apps. But one thing we're actually thinking of is to take the light client and compile it down to WebAssembly, and then embed that in a Chrome extension, which can give a Web3 JS instance to any web pages. So you would actually have a light Ethereum node that gives you really good security guarantees just running in your browser, easy as installing a Chrome extension. So we've begun work on compiling the light client to WebAssembly. It's fairly difficult because it's a very restrictive platform that doesn't have much in terms of the standard library APIs or what have you that exist already. So we would need some glue there on the JS side. But it actually is possible, and Rust is very well suited to that because it's such a low-level language. One of the hardest problems, I would say, for DApp developers using the light client is how we can search those historical logs. So I would say a lot of DApps make requests to a node that look something like, give me all the token transfers from the genesis up until now for this account. And that requires searching all these log events from the very beginning. That's really slow already on a full node, but on a light client, it is really slow. The reason is because we have to fetch all these headers and scan. There's a bloom filter in each header, and we have to scan those bloom filters. And the problem with these bloom filters is that they're limited to 2048 bits, and they're getting more and more full because they don't scale with the gas limit. So you have more transactions, more events, but the bloom filters don't get any bigger, which means the false positive rate goes higher. So you end up getting more and more false positives with each passing day that you download headers and you accidentally download receipts that are actually useless to you. So I'll talk about a few different ways that log searching can be done. So the standard way is basically just download the blooms for, say, block A, B, C, and D, or rather you download the whole header and the bloom is contained therein. And let's say we want to find a bloom filter where bits 2 and 5 are set. So we can just check all of those individually. So this first one matches, this first one doesn't match, the second one does match this filter, the third one does match, and the fourth one doesn't. But you can imagine if you had to do that 5 million times that it could be quite slow. Another approach is to do something that I would call horizontalization, which is for splitting up blocks into batches and then generating a bit vector, or rather 2048 bit vectors, each with the length of how large that group of blocks is. So let's say we're doing it with 4 blocks, and we have 8 bits in this sort of little bloom filter that I'm talking about, but in practice that's 2048. And the entries of these bit vectors are just whether that corresponding bit was set in the bloom of the corresponding block. So we've horizontalized, and now we would check for bits 2 and bit 5. And we can just download those bit vectors, so they look a little bit more like this, and we can check those without downloading quite as much data. The problem is, this doesn't work that well when the blooms are full because we still have false positive rates. It requires a fair amount of overhead on the full nodes to generate or store those historic horizontalized filters because they have to keep them for the historic blocks. And it requires an overhead on light clients to track the hashes or some other kind of reference to those horizontalized filters. So it's not a perfect solution, but it can be an improvement. I'd also like to talk a bit about light clients' role in sharding. So sharding is very hotly anticipated in the Ethereum community. We want to scale, we want to get more transactions. So light clients are actually crucial to that because it's not really possible to be a full node on every shard. There may be some super nodes, but on average, you would just be following 1 or 2 shards and being a light client on others so that you can check that certain receipts or transactions have been produced on other shards that are then coming over to yours, but you don't actually verify absolutely everything there. How are we doing on time? Good? I'd also like to talk a bit about Casper FFG because this is an upcoming improvement to Ethereum's scalability solution. It's like the first step in the Casper roadmap. So Casper FFG gives us finality, so the ability to see whether block hashes have been finalized and won't be reverted. The problem with Casper FFG as it stands is that this justification information about how the validators have voted on specific block hashes is stored in a smart contract. And light clients don't have access to that data easily. So they can't follow this full fork choice protocol of first following the highest justified chain based on the Casper FFG, and then following total difficulty. So it's a bit of a struggle to think of how light clients can fit in with this. Probably they'll just tend to follow the total difficulty-based chain and assume that the justifications will follow that. Or they could have peers send them like compact justification proofs of certain checkpoints in the Casper FFG system. But one thing that light clients can do is fairly easily follow dynamic validator sets under Casper. So again, the light clients can't read the validator set from the contract each block because they don't store the state. So they would, if you have to, every single block, make a contract call to read what the next Casper FFG validator set is, that's fairly difficult. Like, that's a lot of overhead for syncing. But they can still follow chains with dynamic validator sets if changes are only applied on finality. So this is something that's actually like the light client model can already support. So if we have a handoff proof from one validator set to the next, in essence that the previous validator set says this is going to be the next validator set, and then they finalize the block where that statement is made, then a light client can get, just have that whole thing sent to them. So they can see, okay, this block, that statement was made about the next validator set, and then this block is finalized by that previous validator set. So now I know that the set has switched to the next one. There is a slight caveat there if you use that to do an efficient warp sync, where you can just jump to the head of the chain, which is that you can have a prior validator set once they're no longer staked to just stop, they don't have any incentive to keep behaving correctly, so they could sort of just make stuff that was in a really ancient block and just sort of fork off from there and fool you. So that's a little bit of a slight security compromise, but if that doesn't work for your security model, you can always just sync the whole chain. And this is actually especially crucial. This dynamic sets approach is really crucial in a pure proof of stake chain where validators sign blocks. So right now, it's possible just to follow that total difficulty from mining, but when the block verification itself involves checking signatures on a block and not doing proof of work verification, we need light clients to be able to follow that. So just to give a little diagram of that whole thing, you can see first we have a block all the way on the very left, and that's under validator set A. So we say everything before this green line is under validator set A, and the next one is under validator set B. And the first block, we have a signal to the change to be created. And the light client can read that it may be through a log event or something similar. And then a few blocks later, that change is finalized. So any blocks building on that, the light client can then see should be validated under the assumption that validator set B is working on them. So to speak a bit to the developers in the audience, when you build an app on the light client, just what are some pitfalls you can avoid? So the first one, of course, is this ETH get logs. So it's fine when you're watching the head of the chain, especially if you're doing it in a publish-subscribe way, that, okay, a new block comes in, we check a Bloom filter, then we get the receipts if it matches, etc. But if you're going to history, it doesn't really work. So we have a few approaches, which I talked about before. One is to search locally. The other is to search locally with the stored metadata with that horizontalized filters. And the third approach is to have peers search, which, again, we can't always validate because we don't know if peers excluded something. So there's a few trade-offs there, but the fact is none of them are really going to be super fast. Another thing is getting anything by a hash, because hashes don't really leak any information about the block number where any changes occurred. So if you want to get a block by hash, and we have a situation where not everybody stores all blocks, then it doesn't give the light client any information about who they should ask for that data. Likewise, if you're trying to request state data at that block, or transactions or receipts. For example, if you want to get a transaction by hash, and it's an ancient transaction like it happened ages ago, that requires full node peers to store an expensive index of all hashes to the block hash and index where they occurred. And that's already around 2 gigabytes now, I think. For recent transactions, it's usually fine because they'll have them cached, but if you're looking in the history, it just doesn't, it can't be done quickly. And the last thing is estimation of gas. So that's crucial when you're trying to make a call to a contract that you know how much gas it's going to use. But the problem is, because Ethereum smart contracts are Turing complete, we can't predict that beforehand. So it also can vary from block to block because it can be based on how the state has changed in the meantime. So when we're estimating gas, we'll first start with a high upper limit and then a low lower limit, and we'll sort of binary chop to get in the middle. But another annoying thing is that smart contracts can actually see how much gas is remaining and branch on that. So it adds another level of inconsistency to actually the ability to reliably estimate gas. So it should be used sparingly because it can cause a very high overhead on the node, especially if the contract branches in case of different amounts of gas being remaining. For example, if you do your first estimation and then you realize, oh, we can probably go a little bit lower, and you do a second estimation, but the same state proof isn't sufficient for that second estimation with lower gas, you would have to then go to a full node peer and get another state proof, and that's fairly heavy. So I think it's interesting to think about how the light client might fit into the broader ecosystem. So light clients can work on mobile devices. And Whisper, for example, makes a really powerful tool for messaging between peers in a decentralized, anonymous, and private way. And it actually works pretty well for, say, medium latency state channels, not where you have thousands of transactions per second, but maybe where you have one every 10 seconds or anything slower than that. And for example, there's a project called Status, which is already showing how that can be used, that you can have a mobile app that's running a light client and running Whisper for chat, for state channels, for applications. So as far as our roadmap goes for the Parity Light client, you can actually use it today. So you can run Parity with the --light flag in beta releases, and it'll start to sync the chain. If it starts from the Genesis, don't worry. It might take a while because it has to get all those headers. We've already got a pull request open for that essentially hard-coded header hash if you trust that. It is opt-out. So that would get you to the head of the chain very quickly if you trust that hard-coded header hash that's in the client. The UI is still being rebuilt around light client best practices because it takes a lot of effort as a developer to think about what kind of load you're imposing on the local node. And if you're running a full node, you've got everything locally and you don't have those same performance implications. But when you're writing a UI-based Ethereum app around a light client, you have to be very careful about that. And we're also starting the work to compile down to WebAssembly, where you can embed a light client in your browser. So if you're interested in following the progress, all the code is open source. We've got that in the main Parity Ethereum repository. You can follow that at this GitHub link, paritytech/parity. And we encourage you to check it out or even contribute. If you have any questions, now would be the time. Yes? Can you say what are the main differences between the Parity light client version and the Go light client version? Yeah, so the protocols are different, primarily because of this round-trip-based stuff that I was talking about before. So what Go LES allows you to do is have multiple requests of the same kind in a single packet, but not multiple requests of different kinds, where the later ones reference outputs of the priors. The other main difference is with this canonical hash tree stuff. So Go has a canonical hash tree that's generated for all blocks up until now, but now is changing periodically, whereas Parity Ethereum is doing that with smaller canonical hash trees that the light client can generate locally. So it can stay up to date without having to get any trusted information from the developers or other full nodes. Anything else? Well, thank you very much.
So hi everyone. My name is Matan, and I'm pretty excited to tell you about the DAOstack project. I'll let some people take their seats. So in the meanwhile, let me just tell you that this is a result of 4 years of research and development, and finally I think we are ready to give birth to that product. So the name obviously gives the way, right? It's an operational stack for DAOs, decentralized autonomous organizations, but more generally, more broadly, it's an operating system for collective intelligence. Okay, so let me give you some background about the problem, like why we're doing that. So the firm or the company or the organization is orientable but subscalable. And let me define that. So basically the firm is an economical tool. It's a setup to align the interests of many agents, many actors, around a shared goal or shared mission. So that's what I mean by orientable. It's like once you have that setup, you can orient, you can drive that force toward any different goal or mission. So it's orientable. However, it's subscalable, which means that when you grow the organization, when you grow the structure, it becomes less and less effective, less effective per person. So in that sense, it's scalable sublinearly. So I call it subscalable. Now, the free market is another way to coordinate large number of people. And by the way, for the rest of my talk, I will only consider large number of people. So when I say organization, I mean large organizations. So all organizations on the planet are becoming less and less effective. All large organizations on the planet become less and less effective when they grow. But however, free markets are just the opposite. They're super scalable. Free market networks, they become more effective as they grow. But on the other hand, free market is not non-orientable. So you cannot drive the free market to accomplish certain mission. It just grows, right? So with these two definitions, I will define now the DAO. So I know that right now in the space, DAO is used very liberally and in a very wide area of instances. So I will have my little definition of DAO. So I will define the DAO to be this new form of human association, which is both orientable, it can be driven to achieve certain missions, but is also super scalable. It's actually the first organization that becomes more effective when it grows rather than less so. Now, the outcome of being super scalable is that it hits an exponential growth trajectory. So, it's effective, so it grows, but then it's more effective, so it grows faster, and it's more effective, it grows faster, and so on and so forth. So it hits an exponential growth trajectory, and basically eats up the entire container until it reaches the boundaries, and then it saturates. So that's the famous S-curve that any network effect, structure goes. So DAOstack enables global networks to self-organize around shared goals and joint action, combining the scale and efficiency of the largest markets with the alignment and coherence of the smallest firms. So this is the goal. So let me give you briefly, I'm pretty sure you're all familiar with that, but briefly some use cases. So basically, any sort of decentralized application or decentralized autonomous organization that I ever witnessed can fall under this categorization. It's either basically an instance of collaboration, so it can be thousands of open source developers, maybe millions of open source developers cooperating around shared missions, maybe Wikipedia, editors, and so on and so forth, so collaboration. Asset management means that the decision in that organization is about a funneling of asset. It can be a portfolio network, it can be a pension fund or a decentralized insurance network. Curation, of course, well, we're all familiar with curation. Google is the curation engine for websites, TripAdvisors, Booking, and Yelp. The problem with today's crowd curation is that the most important value contributor to the business cycle, which is the curators, is kept outside the business cycle. And that's why I would say the curation capacity is very low relatively. So this is a new stage of curation where you have gigantic networks of curators that are cooperating to create objects, but are also being compensated back with the value that they are creating. And fourthly, the marketplace example, which is a peer-to-peer marketplace. It can be e-commerce, but it can also be ride-sharing. Now, the marketplace is actually the only category that doesn't require a collective decision-making engine, although it can be enhanced with one. So, of course, DAOstack is powered by Ethereum, and basically it's ready to go on the mainnet this month. So I'll show you a demo of the first application on the stack that is now deployed on the Kova network, and we'll have it on the mainnet in the next few weeks. So it's a sort of like pre-MVP stage. So the DAOscape, the landscape of DAOs. So what does it mean? as I said, like every exponential organization, when it hits the exponential trajectory, it just grows to infinity. But then a lot of other instantiations of that are occurring, either with competition on different value systems on the same domain or other domains. So that basically creates an explosion, yet another Cambrian explosion of DAOs, and then you create an ecosystem, and there will be a strong emphasis about the interoperability of those DAOs in that ecosystem. So a word about complex system. There is no way to build a complex system. There is no such thing. So there is no way to build a DAO ecosystem or a DAO no more than there is a way to build a complex system. What you can do is that you can design a complex system by building its elements, then engineering its dynamics, setting up for evolution, and then giving a good initial condition. So that's, if you made a job, that 3 points right, you create an ecosystem or a complex, generally complex system. So if we take that into the DAOscape, we need the elements, so basically the DAOscape letters, the building blocks, the Lego blocks for building DAOs and building ecosystem of DAOs. Then setting up for evolution, for dynamics between elements and dynamics between DAOs, so interoperability of DAOs. And finally, initial condition. So we wanted to achieve super scalable organizations that will require super scalable governance systems. So governance system that can process more and more decisions per number of people as they grow the number of people, which is just the opposite from any decision-making engine that ever was invented. So super scalable governance system will be required to be the initial conditions. So let's start with the DAOstack layers. So ARC is a modular, adaptive, and upgradable governance framework on top of the Ethereum blockchain, and that's basically the DAOscape layers. So this is the atomic unit of governance. We call it smart agency, which is basically a bunch of agents, of actors interacting under smart contracts, or actually a quite large bundle of smart contracts, but under a set of rules. And this is how we think about DAOs. So it's sort of like mesh networks of smart agencies. And this is just a caricature, but probably way beyond that. Much more complex. So let me tell you a little bit about the ARC framework and the smart agency that you can create with them. So this, again, this is the atomic unit of governance. Basically, every element that you're seeing in the image is a smart contract. So every governance system can be divided into the do's and don'ts, right? So the do's is basically if people say such and such, then the collective will do such and such. And the don'ts is no matter what happens, no matter what people say, we'll never do such and such, okay? So the do's, for example, it's like, let's say, give you an example, if 50% of reputation holders vote to approve a transaction of tokens, then the transaction is being executed. Also, by the way, token sale is also goes under this category. If Ether comes into this address, then print token and send it back, right? And the don'ts can be, for example, no matter what happened, this governance unit will not print over 1 million tokens, or no matter what happens, this governing unit will not spend more than 1,000 Ether a month. And note that the global we call that global constraint. The previous one, by the way, we call governance schemes. And note that the global constraints also contain the condition to change the global constraint. So for example, I can be a global constraint saying, no matter what happens, this governance unit will not spend over 1,000 Ether a month, and only governance scheme number 8 can change me. And maybe governance scheme number 8 requires 80% of reputation holders for approval, okay? So you see, in this way, every possible governance system can be coded into this framework, but more so, also the rules to change the rules are part of the rules. And then the actors. So the two top contracts is the token distributor and reputation, or voting power or influence distributor. So they are the internal actors, right? They are distributing the internal tokens and reputation of this agency. And then there is the avatar, which is the external actor. So basically, it's the face of that unit in the world. That avatar can do basically anything that can be done on the blockchain. It can vote as a single agent. So the whole unit, the whole agency can vote as a single agent inside another agency. It can send transactions, funds, and, well, basically can call any function under any contract on the blockchain. So it's the face of the agency. Finally, the controller, which controls the actor and dominated by the governance schemes, confined to the global constraints. Note that there is like 3 dots at the bottom, which are 3 special functions that the controller can also trigger. One of them is changing the list of governance schemes that are subscribed, that are basically allowed to interact with the controller. So basically registering new governance scheme or unregistering an old one. And the second, the same for global constraints. And finally, the third one is transferring the ownership of the so the controller is the sole owner of the actors, and the third one is basically transferring that ownership to a new contract, potentially a new controller, which basically means that this function is upgrading the entire system. So the whole thing, both the protocol level and the technology, is fully upgradable. And finally, universality means that each of the white contract that you see over there is basically universal in the sense that you don't need to redeploy it every time you're deploying a new agency. So the only thing you need to redeploy is the tokens, reputations, and avatars. So in that sense, these modules are serving as a governance as a service sort of thing. So maybe just before going on, just let me emphasize that the Arc contains the architecture for this, like this framework, but also contains the library, like open library of modules with which anyone can fix their own organization. So in that sense, it's kind of like WordPress for organizations. Just as in WordPress, you can pick different modules and plugins and make your own website. Here you can pick different modules and plugins and make your own organization. And then if you are missing some protocol, you can just build a new module, and then everyone can join even a larger library. So the second point was about interoperability of DAOs, and for that we have enhanced Arc towards the full DAO stack. So this is the DAO stack. So at the bottom, of course, there is the Solidity framework, which we call Arc, and then there are shared registries that are supporting interoperability of decentralized applications of various interfaces, which we call archives. It can be the registry that maps. By the way, these are curated registries, so they can basically curate, for example, the entire set of modules, governance modules, or they can curate the entire set of agencies that were created with the platform. Or it can also be just a registry for like interoperability, inter-DApp messaging, for example, or inter-DApp requests. So different interfaces can interact with each other universally, and by that creating a larger network effect. So these are the archives. And then the ArcJS is basically an API layer. It's a library over Web3, which kind of like bridges Solidity to JavaScript, but also make it higher level so that it make it very easy for front-end developers to develop and integrate their collaborative apps to the stack without understanding anything about the blockchain, but also without understanding even the architecture of Arc. Like, you don't need to call different contracts in different order. You can just, with high-level command, you can create and configure organization. You can participate, vote, make proposals, and anything that can be done on the Arc framework. And the result of that is a variety of applications that can integrate and interoperate with each other, the dApps, and we've developed one of them that I'll show you in a moment, which we call Alchemy, with which you can now open more and more smart agencies, and then cloud or mesh networks of those agencies with shared tokens economy basically form DAOs. And of course, then there will be the question, but how do we make them super scalable, right? So we'll answer that in a moment, but before that, let me just show you a really quick demo of Alchemy. So this is the last version deployed on the Kova network. Let's see if the internet permits us. If not, I have I have a video of a slightly older version. Let's see. So the feature to open right now a DAO is disabled. So we just see the DAOs that exist there. So let's enter here. This is the Genesis DAO. This is actually, the Genesis DAO will be the first DAO that will be deployed this month over Alchemy, which will be actually the DAO that is supporting the DAOstack project with its Gen token. So you can see there are like a open proposal over here. So there are the proposal over here, downstairs. Let me see if it works. Yeah. So these are the regular proposals. So they require majority of reputation holders in order to be executed. Sorry. Thanks. Yeah, much better. Yeah, so the proposals downstairs are the proposals that need absolute majority in order to be executed, and then you can, for example, you can vote. Let's vote on this proposal over here, build a plantoid at Burning Man. So now we're submitting it, paying gas for it. So we're just not upvoting it. So the special thing of this protocol, and I'll just mention it in a moment, and then I'll have my second talk tomorrow that I will expand about it, but that's what makes decentralized governance work at scale, is that you can also, there is an additional layer on top of the governance layer, which is a prediction layer. So you can also predict anyone, actually not from within the DAO, anyone can come and predict whether a certain proposal will pass or fail. So let's give a prediction over here that the proposal will pass. And let's pay the gas for it. So once enough predictions are predicting that a certain proposal is going to pass, I think there is another transaction here, then that proposal is basically being boosted, which means that it's open for finite time, shorter finite time, and then at the end of that time period, the decision is being executed irrespectively if there is, irrespective of quorum, basically. So if the majority of the voters, not all the reputation holders, if the majority of voters say yes, it's being executed, if they say no, it's being failed. And that's like the critical part of the holographic consensus, which I will expand about tomorrow. Yeah, so let me not get into too much details here, but you can also create a proposal, of course, and all that. So with that, let me go back over here. So the last piece of this talk is basically mentioning holographic consensus. It's just a teaser for tomorrow. And again, the idea here is how do you make super scalable governance system. So governance system that can process more and more decisions per person when it grows up. So firstly, and again, these are like the two last slides of this talk is kind of like the two first slides of the next talk, not exactly, but just to have something in mind. So what's the problem? Why it's so hard? Why it was never done yet? The problem is that there is a core tension in any decentralized system. There is a core tension between resilience and scale. So if I need to sum it up in one sentence, if you're demanding, if you're acquiring for too much of the collective attention for each and every proposals, then clearly you are not scalable, or definitely not super scalable. And secondly, if you're demanding for too little collective attention for each and every proposal, you're potentially not resilient to faulty behavior. And potentially even both. You can be at the same time not resilient and not scalable. So the way to go about this, to solve this tension is, and we call that holographic consensus, is by allowing small groups of people, so that's what we're doing with the relative majority and the boosting period, allowing small group of peoples making decisions on behalf of the larger majority, but in a way that is cryptoeconomically ensured to be in alignment. Basically what we are doing is that if there is a mismatch between a status quo of a proposal and what people believe is the truth of the DAO, the outcome that the DAO would vote on if everyone will look at it, then there is a potential profit to be made by signaling that mismatch. And that signaling layer is being done with basically the staking layer that I mentioned before, staking against or for a proposal, and that's what that is done with the gen tokens of the project. Yeah, so with that, any questions? Thank you.
The mechanisms for ensuring that people are not doing bad things to the majority.
Sure. I mean, I will get into much more detail tomorrow if you come at 12. So I'll give half an hour just about the full protocol and the logic behind it. But again, basically the idea is that only if enough people are predicting that a proposal is going to pass, only then it's being boosted. And you can ensure by that is that there is, so basically you are crypto-economically monetizing the possible mismatches. So you can make profit by signaling a mismatch. But again, I'll give much more details about it tomorrow. Right. Not to completely ruin the talk.
What is your major difference from Aron what's doing?
Yeah, that's a recurring question. So I don't think we are anywhere different from Aron in our vision. Also, Colony, Jack is over there. And then there's Harbor, and there are now, I think, growing number of players that are sharing the same vision, and also we're in full interaction with each other. I think the differences are eventually in the details. Like eventually you'll just get different architectures, completely different architectures. So for example, our unique element is from the beginning we had a very ecosystemic approach. So we haven't built like an application and then protocol and then build a platform. We started from a platform, like a fully general platform, and when we finished that, we built a protocol, and then we finished that, we built applications. So I think we went just the other direction from all other projects, and we'll see the result if it's better or not, but it doesn't really matter. We're not like, for me, it's not a competition. I think, we have our own design, which is more bottom-up, I would say, more ecosystemic. The second, I think, big differentiator is the holographic consensus. So again, as I said in the beginning, I think DAOs are being used liberally, but what I call DAO is this super scalable organization, and I think that's the first protocol that actually achieves that potentially. So I think these are the two differentiators. Maybe another, a third one is that, again, as I showed the image over there. Again, a lot of DAOs that are being mentioned are more looking at something like that of the form of this, where the DAO, and we've designed the architecture in order to facilitate these kind of DAOs. So maybe it's another third differentiator. Any more questions? Okay. Thank you, Dan. Oh, one more question. Sorry. Yeah.
I'd just love to hear you share some of your daydreams about where this stuff might go. And if we kind of cast your mind 50 years forward, what does the world look like? I know it's all crazy and it's a complex system and things like that, but if you're entertaining the ideas here that could challenge the nation state, I'm just curious how you think about it.
Sure. So I don't think we need to go that far, by the way. I think 5, 10, 15 years is down the road is totally phase changing. So basically, I think you can see how these things evolved in history for different cases. So whenever you created a much more efficient, like multiplicative economy rather than additive economy, or exponential economy rather than multiplicative economy, or super scalable structures rather than sub-scalable structures. So the internet, for example, is an example, right? So basically, once you created that structure, the whole domain of this information distribution completely shifted, right? It ate the entire domain and swallowed all legacy organizations that exist before. I think that the same thing will happen here for the domain of cooperation. So any coordination, any work, but also, as I said, like decentralized insurance. Like once it's a phase transition, it's not, of course it's a process, but a phase transition is a process that suddenly accelerates exponentially fast. And that's what we create here. Once the MVP of a DAO will be created, it will it will run exponentially fast. Initially, exponent looks linearly, but after some point there is like this knee, and then it goes, and that's what will happen. And the outcome of that is that the entire domain of cooperation, of work, of structures, of society, basically, will shift into a completely new form. So just as today we are, dominated by corporations and governments, I think this is completely going to shift to domination by networks, by decentralized networks that actually run the entire economy from bottom to top. So how that looks like, we can spend like an hour about that. Yeah. So yeah, that's a great question. So you should have asked the same question about blockchain, right? Do you think that the elite will allow this transition? And no, they don't. That's true, and that's what's happening these days. Yeah. Okay, we're running out of time, so we'll do that conversation later. Thank you very much.
Goody? Okay. Hello. Welcome. I'm going to be talking about Colony, or some part of Colony today. So before I start, I have to figure out how to change slides. There's an on-off and a no. Oh, it's the other way. Okay. There we go. So I'm going to start with a very brief what is Colony. So Colony, you probably know, is a platform to organize work, to organize collaboration on projects on the blockchain. Our goals are for flexible hierarchies, meritocratic governance, and a lot of these topics we've talked about in the past at DevCon or past conferences. The big picture is that when you have people all over the world, we've got these great tools for cooperating. We have voice chats, video chats, text chats, emails, Slacks in the West, and those are great, but when it comes to collectively managing resources and finances, and things break down. So collective governance mechanisms, they're kind of still missing, and the hope is that maybe now with Ethereum and the blockchain, we could actually harness that power, get that missing ingredient to really form new forms of organization, new forms of work on a global scale. So in our white paper, which was released late last year, we sort of write down our vision of how that might look. This white paper describes in detail the smart contracts that will govern colonies, the tasks, the departments, the voting, the reputation system that I talked about at DevCon. But a lot of what's in here is sort of really describing the smart contracts, how they're going to work, and not so much why. So today I want to talk a little bit about the why, at least of part of this. So if we want to use the blockchain to achieve the goals I mentioned, the problems with the blockchain are, we all know them, blockchains are really slow. So for example, that means that if one click takes 17 or 30 seconds or so, that's a really sluggish interface, and nobody's going to use that unless they're really, really convinced that a blockchain is the best thing ever and they'll have to use it. So this is a problem when you try to onboard users from the Web 2 to Web 3. Also, blockchains are expensive. Every transaction costs money, real money, which people are not used to. So that's also a hurdle. So, and the result is we want to minimize transactions as much as possible. And that's not a Colony thing. That's goes for everyone in this space. So the general principle is you don't really go to the blockchain unless you have to. So one example is if you agree to buy me a beer after this talk, we don't have to go to the blockchain as long as two things hold. One of them is we have an agreement off-chain, and the other one is I can prove it off-chain afterwards if I have to, i.e. if you refuse to buy me a beer. I mean, this is a simplified version, but you'll recognize this is the main thinking behind payment channels, state channels, and all the rest. And the principle is important, so it's in bold. You only go on-chain if there's a dispute, not unnecessarily. Okay, so now let's talk a little bit about voting and collective decision-making. You know, people love to write about voting and talk about voting on the blockchain. You know, you probably when people ask you what's a smart contract, you might even start, well, you know, imagine a multi-sig and several people can suggest spending and then you vote on it and all the rest of it because it's an easy example to give. And, you know, I've certainly done that myself. We get interest from, you know, voting on like boardroom style projects or liquid democracy folks, or, you know, even myself, I wrote an article on voting, and if you haven't read it, do go back and check that out. But why do we love to talk about voting? Well, because it's easy to understand, it's easy to explain, it's relatively easy to implement, and a lot of us think of collective governance and voting as really two sides of the same coin. They go together, you know, like we're collectively governing things means we're voting on things together somehow. But voting is not, you know, a panacea. Panacea? I don't even know how to pronounce that. I've only ever read that. So, problems with voting. Voting is slow. You're going to need at least 24 hours voting period if you have a global, you know, global DAO to allow for all the different time zones. And voting is expensive because all the transactions are going to have costs. And also, thinking about how to vote is expensive. You're going to have to look at what the question is, decide what you think the right answer is, and that is a lot of cognitive overhead and that's really expensive. Like, people's thought is not something we can, you know, we can't just throw out votes to people and expect them to have an answer to all of them. So you really don't want to have people don't want to force them to vote on things that they don't really have to vote on. So the general principle is for a colony permissiveness. Permissiveness means we only vote on chain if there is a dispute. You don't vote on anything a priori. So you don't need to ask for approval. You don't need to wait for someone to assign you to a task. You just do. That's sort of the principle of permissiveness. There should be very little hurdle to activity, to doing things. So zooming in, the smallest part of a colony, of any collective work project, is going to be the unit of work, a task. This is a task in the colony protocol. A task is a smart contract, and it has, you know, several user accounts. It has an administrator, somebody who does administrative managerial duties. It has another description for the work to be done and a due date and some metadata perhaps. There's an evaluator account, which is the user account which is going to get asked to say, was the work done according to specifications? And there's a bounty, of course. There's the reward, which is locked in the smart contract, which gets paid out to the worker account if the evaluator agrees that the work was done, and so on and so forth. So this is sort of the smallest little unit we have to describe. And if you are the worker, and if you submit your work, and your work is accepted, then you get paid after 3 days. And it's this after 3 days I want to highlight, because that's one of the to allow for the permissive nature, you need these delays all over the place, these security delays. So, what is a dispute? We want to balance two things in Colony. We want them to be permissive, which means we want it to be easy to get things done, but we want it to be hard to cheat. And usually what that means is you can do things, but you know, you don't need to apply for permission, so you could just do things. That's it. It should be easy to do things, and it should be hard to cheat means I shouldn't be able to create a task with a description, do nothing, assign a big bounty, assign the task to myself, submit it to myself, and run off with the money. And so what that means is the actions that we can do, they require some reputation and some tokens that need to be staked. Then there are security delays, and so, for example, well, when an evaluator accepts the work, we said there's a 3-day delay before paying out. And anyone who has enough reputation can object to anything that's going on. And I don't want you to think of objections as necessarily I made that task that cheats by trying to pay me you know, for doing nothing. It could just be something simple as, you know, here, this is a duplicate task, should be deleted. So that's an objection. And once an objection is encountered, if nobody else does anything, fine, the objection holds, that task can be deleted. It is only when somebody else comes in and says, no, that objection is wrong, and I counter it, I insist we want to go the other way, it's at that point that there is a dispute, and it's at that point that we vote. So for a dispute to happen, you have to have people stake their reputation and tokens on both sides of a question, and then we have a reputation-weighted vote to resolve the dispute. And even then, we'll try to keep the disputes as local and as small as possible, because you don't want it to have excessive voting. but they can be escalated to a higher domain. I'm going to talk about these points in a minute. And the reputation system deeply integrated in the voting and the incentives for the dispute system. I'm not going to talk too much about that today because we covered that at DevCon. But let's look at this point here. Disputes are resolved as locally as possible. What does that even mean? So if we zoom out a bit, the structure of a colony, we've got domains which you can divide a colony into. That is to divide a huge project into logical subunits, maybe departments, maybe working groups. So for example, here we've got a colony with a development domain, and the development has a Go, a C++, and a JavaScript subdomain. Each one of these domains will have its own budget, and within each domain there will be the tasks that get funded from that budget. And generally, when you do work in, let's say, the JavaScript domain, you will earn JavaScript reputation. That's local. Well, you will earn JavaScript reputation and development reputation and colony-wide. But when there's a dispute in the JavaScript department, it's only the JavaScript developers that get to vote on it at first. So we try to keep that as small as possible. So that's what I mean by that. So disputes can be escalated to a higher domain, but at extra cost, means the following, that if there is, let's say the JavaScript department is small and the reputation distributed within there is kind of lopsided, and there's one person who is aggressively trying to push one point of view that everyone else disagrees with, you can escalate to a higher department. So you can ask all developers to vote on this if you think that the department above, the development department, will agree with you. So you can't appeal to a higher boss, but you can appeal to a larger group of people. But there are risks. It's not, you don't just always escalate whenever a decision goes against what you thought just out of good luck, because there's strong incentives against doing so. You should only escalate if you really think that the rest of the colony will agree with you. And that takes us to this last point, the reputation gains and losses for disputes. So earning and losing reputation, I'm not going to talk a lot about, but I will I want to highlight one aspect of the system. So, okay, in general, yes, you earn reputation by doing good stuff, lose it by doing bad stuff throughout the colony. But one thing is, if you raise a dispute and the vote goes against you in a landslide, like everyone else votes against you, 90% to 10, let's say, then you're going to lose a lot of your stake tokens and reputations that you had to put up to get that vote to happen. Because you should be in communication with the rest of your team, with the rest of your colony. You should have known that everyone else disagrees with you. You're really encouraged to have communication out of bound. But if you do force a vote and you lose it by 51 to 49, your reputation penalty is much, much slighter, because probably it was a good idea to have an explicit vote because it wasn't so clear what everyone was thinking. Okay, so much for tasks. The funding system of the colony, I haven't talked too much in the past, so I'll highlight today, has a similar balance with permissiveness and security. So it should be easy to allocate funding. Even if a person just has a small amount of reputation, maybe you should be able to create a task and assign a big budget to it if that's what it needs, but it should require really long security delays so that if the rest of the colony does disagree, everyone has a chance to see what's going on, so you can't sneakily redirect funds. So again, we have a bunch of domains in a colony, and the general idea is we have a system of funding proposals where funding flows down this hierarchy. So at a certain rate, tokens get reallocated from a higher domain to a lower domain. And this rate depends on, for each of these spending proposals, depends on how much reputation is backing it. So the more reputation is backing a proposal, the faster the tokens flow downhill. And of course, for funding tasks, if you have a bigger bounty on the task, it'll require more time to fill. But if there's more reputation backing the proposal, it'll go faster. So that those two processes balance out the need for security and efficiency. So what we're aiming for is to have a steady and consistent allocation of funds to departments, to working groups, and to tasks, and mediated by sort of a reputation-weighted, preferences. And that's the basic funding proposals, and they govern most or almost all of the day-to-day operations of a colony. There is another way of another funding proposal called priority funding proposal if you want to move funds elsewhere, if you have to pay an external source, if you quickly need to move a lot of funds, like those things can come up. But for that, we need a separate mechanism. A priority funding proposal can move funds between any departments or even out of the colony. There's no rate limitation, but they do require a vote before they pass, right? So that takes care of those. Finally, yes, a note on salaries. We always get asked about this sequence of task-based interactions. That's not really going to be how's that? That's not really going to work for all kinds of work. And it is possible to do things like salaried positions in a colony as well. In fact, many different forms of employment are possible. What the white paper describes is what happens on the blockchain. And the blockchain might only see domains and tasks, but that doesn't mean that when we have humans interacting with the applications that run on the colony protocol that you can't have salaries. So for example, a salary might be realized as a domain with only one member, so you own all the reputation in that domain, you control all the funds flowing into it, and you can always pay yourself out with a fake task whenever you want. So that would then, you know, if you have the right front end, just look like a salaried position, but on the blockchain it's just tasks and domains. And you can do other things as well. You can award people with reputation with fake tasks if everyone agrees. So the idea is, as long as there's consensus, we want to be flexible with the kind of things we allow, just we need to be secure on a game theoretic level. So on the blockchain, it's really just these iterative tasks, but you know, a good front end can make a much more complex and interesting forms of employment. Yeah, and a note on this front end, we are releasing very soon our JavaScript library to our smart contracts that make it easy for anyone to experiment with building new applications that interact with the domains and tasks in the colony system in general. Yeah, so what's been going on? We've had a beta. The colony beta has been running for almost a year, and we've had a second beta starting last December, and it's been closed. That's why you haven't seen a lot of it. It's not been public, but it's been really successful in many ways. It's only a limited subset of what's in the white paper, so we don't have the decentralized governance features yet. It's just the tasks, the bounties, and you know, the automatic accounting on the blockchain, very basic subset, and a front-end application which is like task management with bounties that interacts with the smart contracts on a private network. And interesting to us, we had interest in the beta from all over, you know, the space, the usual suspects, the crypto startups, but also, interestingly, huge organizations thought they could use they'd have use for this, which I found interesting. And they all wanted some way of incentivizing work, farming out work to people, keeping track of who does what, and rewarding them in some way or other. And yeah, so they had use for this even without the decentralized governance. And what we learned is, well, it's hard to assign the value of a task up front, which didn't really surprise us at all. But for the game theoretic safety of the contract as we designed it, you need to have the bounty locked up that can be paid out when the task is finished. So you kind of do need to have that locked up in advance. However, we can imagine a system where you top up the bounties later in a nice front end, and on the back end is just a sequence of tasks. Again, what's on the blockchain doesn't have to be what you see. You know, so the tasks as a smart contract only have the bounty locked up front, but the front end can abstract that away. And yeah, the other thing we found is that the tokens that we were using were in a private testnet. They were worthless and meaningless. And so unless the employer explicitly was willing to exchange those tokens for ether or money or some other form of real value, then people weren't interested in working on the tasks. But that really didn't surprise us. I mean, that's basically what the incentive system of Colony is built on, this idea, right? The rewards. We need the rewards for people to be interested. And yeah, so for the huge organizations, the interest was they could flexibly assign work to a lot of people, and people within the organizations could flexibly pick up work in the system, and the system would automatically keep track of who does what, and that flexibility was valued by the organization that could find unused talent within the organization or idle workers, and the workers benefit too because they can actually move beyond their immediate task set in their immediate department as long as they have time and skills. So this flexibility was valued on both sides. So that was a good thing. Nice to learn. Not what I immediately thought as the first use case of Colony, but there you have it. The current status, well, the beta has been running and we've been incorporating the feedback of all our beta users. We have released our smart contracts. So if you go to this GitHub repo, you can actually deploy them yourself on your own network. You can play around with them. And the JavaScript library that makes it easy to run dApps on the system is also coming really soon. I was hoping to announce it today. Not quite ready, but very soon. That should make it easy for anyone to write dApps on top of the Colony network. We're at Colony. We are writing a dApp to interact with them, but we don't want to be the only one. We're not the gatekeepers, and you're more than welcome to experiment with the smart contracts and with the library to build your own apps. This is where you'll find more information at colony.io. You can sign up for the newsletter, and I know we've been kind of hidden in the last 2 years. We've been developing. We have had a closed beta. We haven't had a lot of big marketing blitzes and token sales, but we're now slowly decloaking after all this time, and we're looking for a lot of really interesting stuff happening in the next half a year, starting with the contract release, library release, and more coming, so do sign up. It's going to be a big year for us. Thank you.